So today I'm going to talk about the project that we did when I was still at the University of Luxembourg with Andreas. It was about extremely light sails, and the idea was to again go far away from the solar system, and this project was supported by Limitless Institute. Since my research interest is into trajectory design, I wanted to use optimal control in order to find trajectories which are the best fitted trajectories to exit the solar system. So this is I'm going to talk about today. So I guess there is no need to talk about how the solar sail works again, but the light being reflected or absorbed by the surface of the sail, it creates a momentum which will push our satellite in the given direction. So when I write the equations of the solar radiation pressure, I can constate that there are two main parameters which will which will influence the magnitude of the resulting force. So these parameters are the area to mass ratio and the distance from the sun. We already mentioned it today. So basically, if I want to have a more efficient solar sail, I either need to build a bigger solar sail, for example, a solar cruiser, which was already mentioned today, and actually less in the afternoon will give some updates about this mission. Or we need to use lighter materials. So for example, a lot of research is done today about aerographite, aerographene materials, which are extremely light because they have very, very low density. The usual materials which are used today is Kepler or Milton. And another parameter which we can play around with is the distance from the sun. Basically, the closer I get to the sun, the more important will be the SRP, the more acceleration I will get, and then I can exit the solar system. So this is the mission scenario that we were interested in. What we will do is that we will consider that we bring our solar sail close to the sun, and then from this point we will start accelerating it and see what is the trajectory that we can find. So here's just some numbers showing the dependence of the final velocity of my sail after 1 year of simulation. So I did one passage at perihelion, and then I see what will be the excess velocity of my sail, given that I have the hyperbolic orbit after 1 year. So we have the closest distance to the sun here. The numbers are very small, but we're optimistic about the materials. Here we have the area to mass ratio. So today, Slava mentioned that something we are aiming is 50 area to mass ratio, but given that we can use maybe at some point even more advanced materials, we can go even further. So this is just to give an idea about how the dependency is. And here we have the final velocity. So the white color here means that we still didn't achieve the hyperbolic velocity after 1 year of simulations. And then you can see that both the distance from the sun and the area to mass ratio has a very important influence on the final velocity. So today I'm going to first talk about the dynamics of the system that I used. Then I'm going to formulate an optimal control problem, something that I do usually. I will present a local optimal solution, and then I will show how the global optimization of the global trajectory changes the performance that we can find, and then make a conclusion. So going back again to solar radiation pressure. I don't like this line. Oh, it's better now. So we have many different components of our solar radiation pressure force, which are the specular reflection or diffuse reflection or absorption. But the final resulting force will be just the sum of all these components. So by changing the orientation angle of my sail according to the sun, I will be able to create different forces in different directions, and all possible orientation will create what I call a force set. So basically all forces that can be created are contained on the boundary of this non-convex drop-like shaped set. What is important here is that the force set that I can achieve is parameterized, is dependent on the optical properties. And here you can see, for example, how different is the control set for an almost ideally reflective sail and for an almost absorptive sail. This actually is important because here we can talk about the questions of controllability again, because for a highly reflective sail, we can create a lot of forces in very different directions, which gives us a lot of freedom, basically, to change the orbit of the sail. But if we have a very absorptive material, right, like aerographene, for example, all the forces are basically aligned with the direction of the solar light. So given this, there are some questions about, can I even change the orbit in the way that I want? And during my PhD, I was actually checking into these questions, and we found out that actually there are some conditions on the minimum reflectivity that your sail has to be able to have in order to change the orbit. For example, there are some orbits around the Earth, like polar orbits, for which if we have not enough reflective sail, we will not be able to change the orbit. So this is something that should be taken into account when we design a mission with solar sails. But this is not the topic of today. The topic of today is this scenario, as I mentioned earlier. So our equations will be simplified because this is just a preliminary analysis. So it's just a two-body problem where I have a drift given by the Keplerian motion, and I have a perturbed motion given by the solar sail, solar radiation pressure acceleration. So as I said, we bring our sail with an elliptic orbit to the sun, and then we start accelerating it. So what is important to take into account is the temperature constraint, because of course we don't want our materials to melt. And the temperature constraint will actually give us some conditions on how close we can get to the sun. And if we check the equations, we can see that the only terms which will be changing is the orientation of the sail, given by the angle beta, and the distance from the sun, given by the term r here. So basically, this term tells me that I can go closer to the sun, but then I should expose less of its surface, of the solar sail, like this case. And the same temperature will be also in the case if I expose the full area of the sail, but I should be a bit further from the sun, right? So I can play around with these two parameters. I cannot constrain the distance because then it will constrain my orientation angle to the sun, and I don't want to do that. So it's important to take into account not the distance constraint, but the temperature. So in order to solve the optimal control problem, I will use the classical tool, which is Pontryagin maximum principle. I will take my equations, I will add the co-states to my equation, and then I will derive the optimality conditions given by PMP. So these conditions allows me to see what is the best control policy in order to maximize something that I want to maximize. In our case, is the excess velocity. So this is the optimal control problem that I want to solve. What I want to maximize is the final energy of my satellite. The equations that I use are, as I said, two-body problem. I have the temperature constraint, and I have some initial conditions, which is the point close to the sun after which I want to accelerate. So first, let me present the local optimal solution. Basically here what we did is that we start from this point. Yellow arrows show the controls, basically, of the sail, so the orientation, the force of SRP. What we do here is that we instantaneously, at each point, will maximize the change of the semi-major axis. This is why we call this solution as a local optimal solution. So as you can see, one passage at perihelion was not enough in order to achieve the hyperbolic orbit. So we will be going on the elliptic orbit, then we come back to the sun, and then at this point where the trajectory becomes violet color, we have the hyperbolic orbit, and then we can access solar system. We can also see it by the jumps with our energy. So we have the first passage at the perihelion, we have the second one, and here is where the energy becomes positive, meaning that we have the hyperbolic orbit. Now let me show you the results for the globally optimized trajectory. So in order to do it, I will do a bit of advertisement of the tools that I've been using. So these were the tools developed by my previous team from Nice, France. They developed the tools to solve the optimal control problem, and we will be using the Julia language, which is a bit trendy nowadays because it's as easy to use as Python and as efficient, closer by efficiency to C++ than to Python. And also it has automatic differentiation. So basically it knows the derivatives of the function, and it doesn't have to use the Euler scheme in order to do that. So we have much more precise results. And it's really easy to use. So when I first solved my problem, we actually have a very trivial solution for this optimal control problem. Basically, the best trajectory that I can get in order to maximize the final velocity is to go into the sun. The question is why? Well, actually, if I check now the constraint that I have on the temperature, well, when I put my sail perpendicular to the sun, I have no exposed area, theoretically, which means that my sail has zero light coming in. It means that I have no heating of the surface, which is, of course, not realistic, because my sail will face the sun and the mission will be lost. So what we need to do is we need to add an additional constraint here, which basically states that I cannot put my sail completely orthogonal to the sun. And this is some realistic constraint, because in reality, you can never have a perfect attitude control, so you'll be always facing the sun. And this is actually the constraint which was also analyzed for the NEA Scout mission, so it's not coming up from nowhere. With this constraint, I will not have such results in my problem anymore. So what I did is that I started optimizing part of the trajectory just to see how the solution deforms. So here, for example, I just optimized the last part of the trajectory. In blue, you can see the globally optimized trajectory. And of course, the difference is not so big, but you can see that we already have some gain in the final energy. If I go further and I optimize the whole trajectory, those are the results. So we have better results, which is already good. So you can see that, for example, if I locally optimize the trajectory, what I try to do is to escape at every moment. But if I do it globally, I know that from one passage at perihelion, I don't have enough energy to exit. So instead of doing the huge circle to come back, I should come back faster, because I don't want to lose so much time. And then I will be able to access the solar system. And again, if we compare the results in terms of the energy, you can see that we really have a big gain in the final energy. So the idea here is that it's also important to know what exactly we want to maximize, because maybe we want to spend more time in the solar system, but it will allow us to have the final velocity, which is faster, and then we'll have a big gain in the final time of the mission. And this will be we can achieve using optimal control. So what is interesting also from the control point of view is that when we analyze the results that we achieved, here I showed on the graphic the temperature constraint. And you can see that here we have a peak, and we have the jumps in the cold state. So in the control, when these things happen, it means that somewhere the solver, when it was solving the problem, had such called touch points. So basically the constraint was touched, and the solver said, okay, we cannot go this way, we should do it a different way. And this is why we have the jumps in the cold states. And this is interesting because what I used here is a such called direct shooting method to solve this problem. The best way to do it is to use indirect methods. But for this, we need an initial guess. So basically, the first phase of solving an optimal control problem is to use these techniques to see how the solution looks like, and then I'll be able to formulate a second stage using indirect methods. But I need to account for the jumps on the cold states. And finally, this is the control policy that I received for the given trajectory. So beta is the orientation angle of the sail. And here we have a peak, but this is just the flip, because once I go to the sun, then the orientation of the sail will be flipped. So this basically states how should I control my sail in order to achieve this trajectory. So to conclude, basically what we did was the preliminary study for deep space missions using solar sails. As I said, we can use shooting methods to improve the results, to optimize again the global trajectory, but to go a bit further. And then what is interesting to do is to to perform a continuation on the optical parameters of the solar sail. So basically here we used an ideal model because this is a very simple model, but of course we should account for non-idealities of the solar sail. And this is something that I did already previously. We can use continuation techniques, basically deform the solution by deforming the optical properties to see what will be the solution for a non-ideal sail. So on that, I finished my talk. And thank you. And you have any questions, please feel free.